All right, so this is video 25 in the behavioral analysis series, and in this video, we're going to talk about uniform continuity. So recall that for a continuous, you have A as a subset of the reals, and you have a function from A to the reals. And then the following two statements are equivalent. F is continuous at every point U and A, and then that's equivalent to bullet point 2, which says for all epsilon and A and for all epsilon greater than 0 and U and A, there exists a delta, and this put in parentheses epsilon and U. All right, so there exists this delta and referencing epsilon and U such that for all x and A, if you have the absolute value of x minus U less than this particular delta, then the absolute value of f of x minus f of u is less than epsilon. So normally I just wrote it in previous videos talking about continuity. We said it like if it's continuous at C for all epsilon, there exists a delta so that x minus c is less than delta, then f of x minus f of c is less than epsilon. All right, so that was continuity. And this is going to be for all points C. Now here, it's just, I wrote delta like this, and we're dealing with U instead of C. The reason why I wrote it like this is that delta actually depends on both epsilon, and in this case, I'm using the letter U. So depends on both epsilon and the value U. All right, so, which I wrote here in blue, in general, delta depends on both epsilon and U and A. The fact that delta depends on U is a reflection of the fact that F may change its values rapidly near certain points, and then may change its value slowly near other points. So it often may be the case that delta can be chosen to be independent of this U and A and will only depend on epsilon. So for continuity just being continuous, the delta depends on both epsilon and U. But it doesn't have to, if there's a way that we can find a delta that does not depend on U, that's what we're interested in. So for this example, f of x equals 2x for all real numbers x. We have the absolute value of f of x minus f of u is equal to the absolute value of 2x minus 2u, and you could factor out the 2, which is equal to 2 times the absolute value of x minus u. So we can choose a delta where delta is equal to epsilon over 2 for any u in the reals. And this choice for delta only depends on epsilon. So it doesn't matter what we have for u, this epsilon or this delta works for all u. All right, so that's a case where we can pick delta to only depend on epsilon. However, there are going to be times where delta depends on both epsilon and u for if it's continuous. So for an example, if you had f of x equals x squared for x is positive, greater than 0, given epsilon, for any u positive, we need a delta so that for all x greater than 0, if the absolute value of x minus u is less than delta, then the absolute value of f of x minus f of u is less than epsilon. So the scratch work would be, we need delta so that when we apply it, we get absolute value of x squared minus u squared to be less than epsilon. And that's equivalent to the absolute value of x minus u times the absolute value of x plus u less than epsilon. So in order to achieve this, we need the absolute value of x minus u to be less than epsilon divided by the absolute value of x plus u. So we need delta to be less than epsilon divided by the absolute value of x plus u. Now, if delta is less than 1, then we know by corollary to the triangle inequality, we have that the absolute value of x minus the absolute value of u is less than or equal to the absolute value of x minus u, which would be less than 1 if we're needing it to be less than delta. But then that would imply that when we add the absolute value of u, we have the absolute value of x is less than or equal to 1 plus the absolute value of u. So there we have, so since we have this relationship, then for here, we have that. So absolute value of x plus u less than or equal to the absolute value of 1 plus u, since we know x is less than or equal to 1 plus absolute value of u. So that be less than or equal to the absolute value of 1 plus u, then plus u, which is going to be less than or equal to 1 plus 2u. So for delta less than 1, if we have absolute value of x minus u less than 1, then we have the absolute value of x plus u to be less than or equal to 1 plus 2u. So we're going to pick delta to be epsilon plus 1, so delta divided by 1 plus 2u. All right, so that way we have that, let's see, so we had x minus u, x plus u. And so we want this, so that's going to eventually be less than, so x minus u, that's going to be less than our delta, which is going to be epsilon of 1 plus 2u times, and then this is less than or equal to 1 plus 2u. So then we get this to be epsilon. All right, so that's a scratch work to find the necessary deltas. Given epsilon, so this is the formal proof, given epsilon greater than 0 and u greater than 0, let delta be the minimum of 1 or epsilon divided by 1 plus 2u. Then for all positive x values for which the absolute value of x minus u is less than delta, we have the absolute value of x minus f of u equal to x squared minus u squared, which becomes absolute value of x minus u times the absolute value of x plus u. Now our x minus u is less than this delta, so it would be less than delta times absolute value of x plus u. And our delta is going to be less than or equal to epsilon plus 2u. All right, so I just changed this to this part. And since we have that the absolute value of x minus u is less than 1 implies that the absolute value of x plus u is less than or equal to 1 plus 2u, then the following line and smiley face, we get that this is less than or equal to epsilon over 1 plus 2u times 1 plus 2u, which equals epsilon. So the point is that for this example, delta depended on u, whereas the example before, we had delta depend on just epsilon. So now we're going to go into uniform continuity. So for uniform continuity, we need a single delta that's going to work no matter what u value we're at. This delta is going to solely depend on epsilon. And so at uniform continuity, f is uniformly continuous over A if and only if, for all epsilon, there exists a delta, so that for all x in u and A, the absolute value of x minus u less than delta implies that the absolute value of x minus f of u is less than epsilon. So very similar looking definitions. Now, this one that we did here, we had epsilon or delta only be depending on epsilon. And so this one is one where it's uniformly continuous. Now this one, we had our delta chosen where it's going to always be dependent on what u you're at. So this is not uniformly continuous. Okay, so the definitions are really similar. So let me write down the continuity one. So regular continuity. So we have for all epsilon and any u, there exists a delta, and this delta is dependent on both epsilon and u, so that for all x, the absolute value of x minus u less than delta implies that the absolute value of f of x minus f of u is less than epsilon. So the order in which we list the values, so here we have delta listed after epsilon, and here we have delta listed after we've listed u and epsilon. So that's an important distinction. And the main point is that for uniform continuity, delta only depends on epsilon, does not depend on both u and epsilon. Now for sequences, if you have two sequences, xn and yn, if the limit of the difference of xn minus yn is equal to 0, then the limit of f of xn minus f of yn is also equal to 0. So that's a way to test for uniform continuity for sequences. Now, if it's not uniformly continuous, then we change these quantifiers. And so it's not uniformly continuous if there exists an epsilon, so that for all delta, there exists x and u and a, where the absolute value of x minus u is less than delta, but we have the absolute value of f of x minus f of u is greater than or equal to epsilon. For the sequences, we'd say there exists two sequences, xn and yn, where the limit of the difference of the two is 0, but the limit of f of xn minus f of yn is not equal to 0. So from earlier, we had f of x equals x squared for x greater than 0 is continuous, but the delta chosen depended on both u and epsilon. Now for larger u values, delta gets smaller. And and larger points of f of x equals x squared give steeper slopes. So for a fixed epsilon, the required delta should get smaller and smaller as u gets larger and larger. And so for our function f of x, x squared being on the domain 0 to infinity, and the fixed epsilon, we cannot pick a single delta that's going to work for all u and x. However, let's say we had the domain being the closed interval 1 to 4. The steepest the slope gets within for this interval is going to be at the endpoint 4. Now we haven't gone over the derivative, but we know that from Calc 1, we know the derivative of x squared is 2x. And when you evaluate the derivative at 4, f prime of 4 is equal to 8. And right, the derivative corresponds to the slope. And so that value 8 is going to be the largest value for the slope of the function x squared in that interval. So the slope is never going to be more than 8. So for any epsilon, pick delta to be equal to epsilon divided by 8. Then we have for all x and u in the closed interval 1, 4, x minus u less than delta implies that f of x minus f of u, which is x squared minus u squared, difference of squares, so that's going to be x minus u times x plus u, and that's going to be less than delta times 8, right? Because for x plus u, we have that x plus u is going to be less than or equal to 8. And so we have x minus u, which is going to be less than delta times 8. And our delta is epsilon divided by 8. So then we have epsilon divided by 8 times 8, which is equal to epsilon. All right, so this was a case in which we changed the domain to be a closed interval 1 to 4, and that made this uniformly continuous. However, if we had the open interval from 0 to positive infinity, it cannot be made uniformly continuous. All right, so these are 3 examples, and we're going to show either it's uniformly continuous or it's not uniformly continuous. All right, so let's do the first one. And this one's, I mean, we already did it for the closed interval 1 to 4. It's going to be sort of similar. Now we're doing with the closed interval 0 to b. Okay, so we need to show uniform continuity. So we need to show for all epsilon, there exists a delta. This delta is only going to depend on epsilon. So that for all x and u in the closed interval 0 to b, absolute value of x minus u less than delta implies that the absolute value of f of x minus f of u is less than epsilon. All right, so that's, I just wrote down the definition. Okay, so now what is this? F of x minus f of u. That's the absolute value of x squared minus u squared. which we know difference of squares is absolute value of x minus u times x plus u. And we need this whole thing needs to be less than epsilon. And we know the x minus u is going to be less than whatever delta we choose. That's going to depend on epsilon. Now note that for all x and u in this closed interval, we know x is less than or equal to the endpoint b, u is less than or equal to the endpoint b. So when we add x plus u, that's got to be less than or equal to 2 times b. All right, so then I think now it should be obvious what we're going to pick for delta. So we're going to pick delta. So let me make this formal. So given epsilon, we're going to choose delta to be equal to epsilon divided by 2b. Then for all x and u in the closed interval 0 to b, we have that if the absolute value of x minus u is less than delta, then the absolute value of f of x minus f of u which is x squared minus u squared, which is x minus u times x plus u. And then this is going to be less than our delta. Our delta is epsilon over 2b. And then this is less than or equal to 2b. So the whole thing is less than epsilon over 2b times 2b, which gives us epsilon. So thus f of x equals x squared is uniformly continuous on the closed interval 0 to b. All right, so hopefully that wasn't too difficult. Now the next one, we're going to show that f of x equals 1 over 1 plus x is uniformly continuous on the closed interval 0 to 1. And I'll do a different color for this one. All right, so let's do a sketch. Again, so uniform continuity. All epsilon, there exists a delta. So for all x and mu in this closed interval 0 to 1, we have that the absolute value of x minus u less than delta implies that f of x minus f of u is less than epsilon. All right, so that's just the definition. Now, all of our x and u's are in the closed interval 0 to 1. Now, what is f of x minus f of u? So our function is 1 over 1 plus x. So this will be 1 over 1 plus x minus 1 over 1 plus u. And we could do some algebra, write this as one fraction. So the fraction is going to become, so 1 over 1 plus x, that does not have the other denominator 1 plus u, so it's going to be 1 plus u, and then minus, and then 1 plus x divided by 1 plus x times 1 plus u. So we have the 1 and minus 1 cancel out, so you just get u minus x. Over 1 plus, and we could break it up so that this will be less than or equal to absolute value of u minus x, or same thing as x minus u, divided by 1 plus x times 1 plus u. And we need this to be less than epsilon. And so we got to figure out a way so that our delta is only dependent on epsilon. And we know we have u minus x, which is x minus u. That's going to be less than delta. So it'd be like delta over 1 plus x times 1 plus u. So how can we choose delta so that it's not dependent on anything but epsilon? So we have our intervals 0 to 1. And so we know that x is greater than 0, u is greater than 0. And so if we do, notice we have 1 plus x and then 1 plus u. So then we have x plus 1. What's the largest? So that's going to be, smallest it's going to be is 1. So that's greater than or equal to 1. Well, what does that mean? If I take reciprocal, then 1 over x plus 1 is less than or equal to 1. And then same thing for u. U plus 1 is greater than or equal to 1. Taking the reciprocal, 1 over u plus 1 is going to be less than or equal to 1. And so this is less than or equal to absolute value of x minus u over 1 times 1, right? So really it's just dividing it by 1. So then we could choose delta to be epsilon itself. All right, so hopefully that makes sense. So now the actual proof, and I'll go ahead and I'll do it in green. Given epsilon, pick delta to be equal to epsilon. Then for all x and u, and the closed interval 0 to 1, we have that if absolute value of x minus u is less than delta, which we know is epsilon, then f of x minus f of u, which we said was equal to absolute value of 1 over 1 plus x minus 1 over 1 plus u. And we did some algebra, and we got this whole thing to be less than or equal to the absolute value of u minus x. divided by the absolute value of 1 plus x times the absolute value of 1 plus u. Make these absolute values a little bit more obvious. Okay, and we know each one of these, 1 plus x and 1 plus u, those are, each one of those is, since we have it as, maybe it might help to write it like the following. So this is actually equal to yeah, I'm going to write it like this. So this would be less than or equal to the absolute value of u minus x times 1 over x plus 1 times 1 over u plus 1. And we know that 1 over x plus 1 is less than or equal to 1. 1 over u plus 1 is less than or equal to 1. So this will be less than or equal to absolute value of u minus x times 1, or just the absolute value of u minus x. And we know that's less than delta. So this is less than delta, which is epsilon. So hopefully that string of inequalities makes sense. So I broke it up as the absolute value of u minus x times 1 over x plus 1 times 1 over u plus 1, because each one of these was less than or equal to 1. So that's why it'd be absolute value of u minus x times 1. All right, so then that itself is less than delta, which is equal to epsilon. All right, so that's the answer for that one. All right, and so this example, last example for this video, show that f of x equals 1 over x is not uniformly continuous on the interval from 0 to 1, where it's open around 0 and closed around 1. So we've dealt with the previous two, we're dealing with showing it was uniformly continuous. So there's either two ways we could do this. We could either do the negation of it being uniformly continuous, that definition. So it's not uniformly continuous, and there's two things we could use. That there exists an epsilon for all delta. There exists x in u, so that x minus u is less than delta, and the absolute value of x minus f of u is greater than or equal to epsilon. All right, that was just a negation of the definition I was using for the previous two. Or there's also for uniformly continuous with sequences, for all sequences xn, yn, the limit of xn minus yn, so the difference between the two shrinks to 0, then the limit of f of xn minus f of yn is also 0. All right, so that's sequential version for the uniformly continuous. So not uniformly continuous, we would say there exist two sequences, x and yn, or the limit still goes to 0 for xn minus yn. But we have the limit of f of xn minus f of yn is not equal to 0. All right, so I'm going to use this one. It's just easier, in my opinion. If we're going to show it's not uniformly continuous, I'm going to use this. So I just need to produce two sequences where the limit of the difference is 0, but when you evaluate the function for the sequences, the limit of those, that difference is not equal to 0. So our function is 1 over x, and we have the interval 0 to 1, where 1's a close and u is, or 0 is open. So consider the following. I just need two sequences. So consider xn to be 1 over n. Consider yn to be 1 over n squared. So then the limit of xn and yn that's going to equal 0 because this goes to 0 and that goes to 0. So that goes to 0. But if you do f of xn, that's 1 over n, which equals n. If you do f of yn, it's 1 over n squared, which is n squared. So, but limit of f of xn minus f of yn which is equal to f of xn turns into n, so that's the limit of n, minus n squared, because f of yn is n squared. All right, and as n goes to infinity, this goes to infinity, so this is not equal to 0. So we produce two sequences, xn and yn, where you have a sequence 1 over n and the sequence 1 over n squared. Those go to 0, so the difference between them is 0 for the limit. But when you evaluate the function, it goes to infinity for the difference of the limits. So therefore, it's not 0. So this is not uniformly continuous since I was able to produce that. All right, so that's where I'll stop this video.